Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element lead. Lead is a grayish silvery color. Let me magnify this for you. But I don't have to show you a tiny sample in a tiny vial. I have a much larger sample I can display. It's my density cube that you'll see a little bit later on, or even in this roll of solder, or even a smaller sample in this old-fashioned glass fuse. But let's get back to our slides. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Lead is the 82nd element in the periodic table. Its atomic number is 82 because that's how many protons are in its nucleus, and that's what distinguishes it as a unique element. Lead is one of 11 or so elements discovered prehistorically because it occurs, though rarely, in its native form on the surface of the Earth. It was discovered early enough that I can't detail its discovery, but that won't stop us from discovering lots of fascinating things about this element. Lead is mentioned in the Bible, in Exodus, when Moses, led the Israelites out of Egypt. After crossing the parted Red Sea, it crashed down on Pharaoh's soldiers, and we see this quote, "But you blew with your breath, and the sea covered them. They sank like lead in the mighty waters." So we know lead was known very far back in history. Alchemy, early explorations into the nature of the chemical world, while steeped in mysticism, really gave modern chemistry a jump start. Alchemists were fascinated with the transmutation of one substance into another, especially base metals such as lead into noble metals like gold. While we can do that today, uneconomically, with particle accelerators, it was completely beyond the alchemists of the time. This oil on canvas is The Alchemist by David Teniers the Younger, painted in the mid-1600s. While the derivation of the word lead is somewhat debatable, the chemical symbol Pb derives from the Latin word plumbum, from which we get the words plumber and plumbing, since lead pipes were used in that profession. A major source of lead is the mineral galena, which is lead sulfide. It occurs in incredibly shiny cubic crystals, far more beautiful than the dull gray we usually associate with the metal lead. Estimates are that in 2019, the world produced around 4.72 million metric tons of lead. 4.72 million metric tons of lead would be a cube, 7.5 meters on a side. Let's throw an average person in there for comparison. Lead is actually the fifth most used metal by tonnage after iron, aluminum, copper, and zinc. World lead production looks to have grown exponentially, at least since 1840. Most of that lead is mined in China, with 42% of the world's production. Australia, Peru, Mexico, Russia, India, and the U.S. are also significant producers. About 1/2 of lead production comes from recycling. Lead is a shiny grayish-silvery metal when freshly cut, but it quickly tarnishes to a dull gray when exposed to the air. Currently, lead is going for about $2 per kilogram, one of the cheaper elements we've seen so far, and, as usual, prices depend on purity and quantity. According to the U.S. Geological Survey, here's how the price of lead has varied from 1900 to 2019 in inflation-adjusted 1998 dollars. As you can see, lead has always been between about 60 cents and $2.75 per kilogram, and seems to have avoided the wild swings and exorbitant prices of many other elements. Lead seems to be quite a bargain. The element lead is pretty uncommon. Coming in as the 33rd most abundant element in the universe by mass, it makes up 1 part per 100 million. About as abundant in the Sun, it also makes up almost 1 part per 100 million of its mass, and is the 35th most abundant element there. It's the 37th most abundant element in meteorites at 1.4 parts per million. 10 times as common in the Earth's crust, it's the 36th most common element at 1 part per 100,000. Lead is rarest in the oceans of the Earth, making up only 3 parts per 100 billion, the 60th most abundant element there. Lastly, by all rights, there should be no lead in us, since it serves no biological purpose, but because we live in an environment with this element, it does make up 1.7 parts per million of our mass. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Lead is here. I understand this looks complicated, but let's look at just lead a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of lead created by various processes relative to the Sun. Almost 96% of lead present today is believed to be produced by dying low-mass stars, the magenta area. The rest is produced in supernovae, the yellow area. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 82 protons for lead, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 38 known isotopes of lead, and of these 38, there are 4 stable non-radioactive isotopes. These lead isotopes occur in nature in the amounts you see here, most of which is lead-208. The heaviest nucleus considered to be stable is lead-208, and all elements beyond lead in the periodic table are radioactive and have no stable isotopes. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of lead occupy the same place in the periodic table. Of the radioactive isotopes of lead, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest lead half-life is lead-205, with a half-life of 17.3 million years. This seems long, but compared to the 13.8 billion year age of the universe, it's not even a blink of an eye. That's why we don't see any of these isotopes out wandering around in nature. They've all decayed away. If you want to experiment with these, you have to make them in a reactor. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If you wait one half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice that there's one remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. I want to show you the decay series that leads from uranium to lead, and I want to do it on a chart you'll see in many physics texts. We're only using a very small portion of a much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us what element we're dealing with, each row is one unique element. Generally speaking, when an isotope decays, it can do this by emitting an alpha particle or a beta particle, and I'm oversimplifying this. An alpha particle is made up of 2 protons and 2 neutrons, 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium atoms have 88 protons. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, and the electron is spit out of the nucleus as a beta particle. This means that the nucleus gains a proton, but does not change its atomic weight. This time, we'll start with thorium-234. Gaining a proton, but not changing atomic weight, moves us up 1 row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Now, let's look at the complete uranium decay chain. We'll start with the most common uranium isotope, uranium-238. Uranium-238 has a half-life of 4.5 billion years. I've listed the half-lives at the top, but I'm not going to recite them anymore. Uranium-238 decays by alpha into thorium-234. Thorium-234 decays by beta. Remember, we move up 1 square for beta, into protactinium-234. That decays by beta into uranium-234. Note, this uranium is a different isotope than the one we started out with. Uranium-234 decays by alpha into thorium-230. Again, a different isotope than the thorium before. Thorium-230 decays by alpha into radium-226, which decays by alpha into radon-222, which decays by alpha into polonium-218, which decays by alpha into lead-214. This is a radioactive form of lead, which decays by beta to bismuth-214, which decays by beta to polonium-214, which decays by alpha into lead-210, another radioactive form of lead, which decays by beta to bismuth-210, which decays by beta to polonium-210, which finally decays by alpha to lead-206, which is stable and not radioactive. Quite a roller coaster ride from uranium to lead. Lead-206 accounts for about 1/4 of the lead on Earth, if you remember. Since Earth is about 4.5 billion years old, about 1/2 of the uranium-238 on Earth has decayed to lead. There are other decay chains that also end in lead, but instead start with thorium-232 or uranium-235, among others. Here's the thorium-232 decay series. Some isotopes can probabilistically decay by both alpha and beta emissions, and this complicates the last stages of this chain a bit. I didn't show those in the previous chart for simplification. It doesn't change the end result. Here, we start with thorium-232 and end up with lead-208, not the lead-206 we just saw in the uranium-238 series. And here's the uranium-235 decay chain, sometimes called the actinium decay chain. Again, this chart is somewhat more complicated with even more isotopes which can probabilistically decay by both alpha and beta emissions. Here, we start with uranium-235 and end up with lead-207, yet another different isotope of lead than we've seen before. Now we've seen 3 of the 4 naturally occurring isotopes of lead being the result of nuclear decay: lead-206, 207, and 208. The last and least abundant isotope of lead, lead-204, is either created in dying low-mass stars or as the result of the decay of polonium-208. Lead has a fairly high density at 11.34 grams per cubic centimeter. As a reminder, water has a density of only 1 gram per cubic centimeter. I've put up more densities for you here. Most people consider lead as being a pretty dense element. Here's a graph of the elements from highest density to lowest density. I have a set of blocks, like I've shown you, so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, lead's density is 11.34 grams per cubic centimeter, the magenta circle. Given lead's low cost, my lead block is cheap, a little over $4 worth. Lead has a very low melting temperature of only 327 degrees Celsius. It has the 30th lowest melting point, and 12 of those 30 melt below room temperature. You could easily melt this stuff on your stove if you weren't worried about making a toxic mess of your kitchen. Lead boils at a fairly low 1,749 degrees Celsius, or 3,180 degrees Fahrenheit, giving it the 58th highest boiling point, or the 37th lowest boiling point, of all the elements. That's about 1,422 degrees Celsius above its melting point, giving it the 57th largest liquid temperature range of all the elements. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest, so here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range, all the way down to neon, which is liquid only in a 2.51 degrees Celsius range. Again, lead has the 45th narrowest liquid temperature range at 1,422 degrees Celsius, about in the middle of the pack. Notice all the noble gases, and hydrogen have a very small liquid temperature range. If we compare the size of the lead atom to that of hydrogen, we'd see something like this. The lead atom is about 3 times the size of hydrogen. Here is its electronic structure. By the way, a picometer is a trillionth of a meter. Atoms are enormously small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. Lead has the 49th largest size atom of the elements, also about in the middle of the pack. Lead has a pretty high thermal expansion rate. As a matter of fact, it has the 10th highest rate of all the elements, a whopping 3 parts per 100,000 per Celsius degree. This means if I had a 1 meter long bar of lead and heated it by only 1 degree Celsius, it would get longer by 3/100ths of a millimeter. That's about a hair width, and that's only heating it by a measly 1 degree Celsius. Lead expands about the same as zinc and 30% more than aluminum. Lead is amphoteric, meaning that chemically, lead-containing molecules react both with acids and bases. Here you see 2 reactions, both with lead oxide, one reacting with an acid, hydrochloric acid, and the other reacting with a base, sodium hydroxide. While lead is not unique among the elements for this capability, it's still not typical. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. Lead has a relatively simple visible spectrum, almost boring. Let's increase the contrast to show you the specific colors. Only a few bright colors in the red, green, and blue parts of the spectrum. If you burn lead salts in a flame, the red, green, and blue colors will combine to a bluish-white flame. Don't do this at home. Creating lead vapor is a severe health hazard. This spectrum uniquely identifies the element as lead to scientists. No other element gives off this set of colors. Let's take a look at a few applications of lead. Unlike many of the other elements here in the upper reaches of the periodic table, there are, or were, quite a few uses for this metal, most related to its high density, easy workability, low melting point, availability, and cost. This is a decorative pipe, but not for plumbing, rather for smoking. But you'd have to be crazy to use a lead pipe for this, or you'd become crazy. Lead has been alloyed with many other metals for many different purposes. Lead alloyed with tin was originally called pewter, though that formulation, at least for items coming into contact with the human body, has been modified to exclude lead because of its toxicity. Modern pewter is a combination of tin, copper, and antimony. Fusible alloys are easily meltable at relatively low temperatures. As the name implies, they're useful in fuses, like this one you might find in your car, or this one you might find in electronic gear, or these old-fashioned ones you might find in an older house, or, if you ran a power station, this somewhat large version, not to scale. They all share a common trait. Let's look into the top of the home fuse to see it better. They all have pieces of fusible alloy. The electric current, for whatever they power, passes through this alloy acting as a wire. If too much current is drawn, the fusible link heats up and melts, breaking the circuit and saving your house, or whatever, from burning down. Speaking of fires, low-temperature fusible alloys also protect your buildings. Some fire sprinklers have 2 plates connected with low-melting alloy. When the temperature rises above a certain point, the plates come apart, releasing the water to put the fire out. Similarly, fusible links have cables attached to them. In a fire, the two halves melt apart and close dampers and doors. Because of lead's low melting point, it was used extensively in the electronics industry to solder metal parts together. Here, you see electronic parts being soldered to copper pads on a prototyping circuit board. Plumbers use solder for the same purpose, to solder together copper pipes. Up until 1986, most solder contained 60% tin and 40% lead. Many people thought soldering together drinking water pipes with lead-containing solder may not be a very good idea, so that was outlawed, and in 2006, many countries, and California, banned lead in plumbing. Its use in electronics was banned too, because it was appearing in landfills. Now, we use lead-free solder that's a combination of 99% tin, 0.3% silver, and 0.7% copper. Printer's type used in letterpresses is made mostly from lead, but because, as we've seen, lead is so soft, it's hardened up by adding in some antimony and tin. This alloy was easy to cast because of its low melting point. It also completely fills all the nooks and crannies of the casting mold. Notice each letter on its own little piece of lead. Making up a block of text was a laborious task. We don't do these tasks much anymore since computers have taken over these jobs. All we have to do is type. We may have lost some of the elegance of lead type, but there's no on-the-job lead poisoning either. If you ever went into a printer's shop, my dad was in printing, you'll see type cabinets like these with each drawer containing a specific font at a certain font size. These drawers were organized in some way that made sense to printers, but I could never figure out. Slightly less laborious were linotype machines. Here, the operator sat in front of a keyboard and typed the text. Liquid type metal was instantly cast into lines of type that were then mounted in the printing frames. Far less work than dealing with each letter individually, but you were sitting alongside a fuming pot of lead all day. That couldn't have been healthy. Remember that lead mineral, galena, or lead sulfide? It has semiconducting properties that let you use it as part of a crystal radio. On the left, you see a small piece of galena embedded in a little solder-filled metal cup. On the right, you see that little cup with a wire positioned to touch the crystal. Certain spots on the galena crystal act as a diode, allowing electricity to flow in only one direction. This allows electromagnetic radio signals to be transformed into an electrical audio signal. This arrangement of a thin wire and the galena crystal is called a cat's whisker. Here's a complete crystal radio on the left, minus the very long antenna you attach to it, and a close-up of the cat's whisker on the right. You'll often find lead hammers in a machine shop. The heavy lead gives you a good wallop, and the soft lead won't damage the part or the machine you're working on. Most glass you encounter has no lead, but there is glass that does contain lead. Lead glasses contain between 4 to 60% lead oxide, which is clear when in the glass itself. In modern versions of lead glasses, the lead oxides have been replaced with other metal oxides, such as titanium dioxide and zirconium dioxide, to keep the lead out of the environment upon disposal. However, adding lead to glass gives it interesting, useful, and beautiful characteristics. First, it increases the bending power, or index of refraction, of the glass. Whereas light entering normal glass bends a certain amount, light entering lead glass bends more. This adds to the sparkly nature of cut glass objects. For illustrative purposes, I've exaggerated the amount of bending for the lead glass. In reality, they only differ by 3 degrees. The window glass shows the proper bending. Second, dense lead glass makes better rainbows. That quality is called dispersion. So if you have a prism made from normal window glass, it produces a narrow spectrum. A lead glass prism spreads out the colors more, making a wider spectrum. Lead glass is therefore more useful if you're building a spectroscope like this one. See the prism? Because lead glass is better at making rainbows, it was valued in the making of various crystal glass objects like chandeliers and glassware meant to sparkle in the light. Swarovski has created an entire business around this phenomenon. These are lead acid batteries. This is the major application for lead, with 80% of the lead produced going to their manufacture. You probably have one of these in your car. On the left, you can see a few of the lead metal plates inside one of these batteries. Like all products containing lead, these must be recycled properly, and indeed, lead in batteries is the most successful recycling story to be told. 96% of battery lead is recycled, mainly into new batteries. Compare this to paper, 73% recycled, aluminum cans, 54% recycled, tires, 50%, and glass bottles, only 25% recycled. One use of lead, for its dense nature, is in projectiles. The dense lead resulted in a large wallop for a small volume projectile. They were easy to cast due to the low melting point of lead. The ball on the left is a musket ball dating back to Napoleonic Wars in the early 1800s. The middle bullet dates from the Civil War, and the bags on the right contain lead shot, tiny lead pellets which get loaded into the business end of a shotgun shell. Lead is no longer used for these purposes because of the toxic nature of the metal polluting the environment. I suppose lead bullets can cause lead poisoning over long periods or over very, very short periods if you are the target. Using lead for projectiles isn't a modern invention. This is an ancient Greek lead sling projectile with a winged thunderbolt molded on one side and the inscription decay, meaning take that or catch, on the other side. Apparently, the ancient Greeks had a good sense of humor. If you fish, you know that lead weights, or sinkers, were used to make sure your hook went to the bottom where the fish were. Often, when the fish were caught, the lead weights would drop off the line and remain at the bottom of the lake or ocean. This was a serious pollution problem, and other metals like steel or bismuth have replaced lead for this purpose. Historically, lead has been used for pipes because of its highly workable nature. Turns out this was not such a good idea due to the toxicity of lead. We're all familiar with the problems Flint, Michigan had and continues to have due to its lead pipe infrastructure. The U.S. government is dedicating billions of dollars to removing all lead piping. Thomas Midgley Jr. may be one of the most notorious poisoners in human history. He worked for General Motors in the 1920s. Internal combustion engines of the time had a problem called knocking, where the compressed air gas mixture would detonate prematurely in the cylinder. Midgley added a chemical, tetraethyl lead, to the gasoline to increase the combustion temperature and prevent premature detonation or knocking. He was completely aware of the toxic nature of tetraethyl lead. Indeed, many workers on the project died of lead poisoning, and Midgley himself suffered non-lethal lead exposure, but he continued to promote its use. GM ignored the fact that adding simple ethyl alcohol would do the trick because they knew they couldn't patent that solution. They even went as far as calling the chemical ethyl, leaving out any reference to the lead content because everyone was already familiar with the effects of lead. Leaded gasoline continued to be sold in the United States until the mid-1970s when it was banned, mainly because catalytic converters were mandated for cars and the lead poisoned even the catalytic converter. But the damage was already done, and leaded gasoline was responsible for the worst case of worldwide environmental lead pollution. Leaded gas was finally banned worldwide in 2021. If that wasn't bad enough, Midgley was also responsible for the invention of chlorofluorocarbons, or CFCs, often called Freon, used in refrigerators and air conditioners. CFCs are responsible for the destruction of the ozone layer and for increasing global climate change. Midgley has been called a one-man environmental disaster. You may have heard the expression of something or other going down like a lead balloon, meaning something destined for failure. However, the Mythbusters prove that if you're careful and pay attention to the laws of buoyancy, you can actually make an 11-kilogram, 24-pound lead balloon float.
Dude, that is a lead balloon.
I am really pleased. We might have been able to get away with a smaller balloon, but this is a lead balloon. We did it.
That worked beautifully. It's perfect.
Although we call the stuff in pencils responsible for making the marks lead, it's really just the more innocuous element carbon. In the 1680s, graphite was called black lead, and the name stuck. The power of marketing. Lead, because of its density, is often used to absorb radiation. Radiation can be in the form of alpha particles, which can be absorbed by even a piece of paper. Beta particles, a little more penetrating, which can be absorbed by a sheet of plastic or thin metal. And finally, the highly penetrating X-ray and gamma ray, which requires a thicker layer of dense metal, such as lead. Perhaps you've had a dental X-ray, where the dentist has protected the rest of your body with a stylish, heavy apron containing lead, similar to the ones being modeled on the right. Your dentist may have even used a lead-containing shield around your neck to protect your thyroid. A sample of this is on the left. If you had to reach into an active X-ray machine like a fluoroscope, you might wear one of these on the top of your hand to prevent exposure, according to Theodore Gray. But it looks more to me like something you might use to immobilize a hand into a specific position by bending the very soft lead metal. But I really trust Teo. Hospitals routinely work with radioactive isotopes for various diagnostic and treatment procedures. These isotopes are transported in lead-shielded containers to protect workers and patients. These are often called pigs because of the way lead is cast into ingots, with the ingots feeding off a central source, like piglets feeding from their mom. In labs and larger situations, such as reactors and particle accelerators, lead bricks, like the one behind me right here, are used to shield operators and researchers. On the left, you see an entire room made up of these bricks. Originally, the Golden Gate Bridge was painted with red lead paint, a lead oxide compound. The pigment powder has a beautiful orange color used in the Golden Gate Bridge paint called International Orange. I've put up the CMYK values for you if you want to reproduce the official bridge color for yourself. Red lead pigment is still available to artists and has been in use since the 1500s, but it's no longer used to paint the Golden Gate Bridge. Incorporating lead into paint yields a paint that better resists weathering. White lead paint, consisting of lead carbonate and lead hydroxide, was easily combined with other pigments to make any color the customer desired. This lead compound was also used in cosmetics, as we'll see in the next slide. One unfortunate problem is that when the paint did age and flake, the toxic flakes went into the environment and poisoned people around them. Children were especially susceptible. Lead paint is now banned for virtually all industrial uses. Elizabeth I of England was commonly depicted with a whitened face. The same pigment in white lead paint was also used in face whiteners and is thought to have contributed to her death. One case of lead poisoning that's been in the news lately was of Ludwig van Beethoven. Beethoven died in 1827 at the young age of 56 from a variety of ailments which included severe hearing loss in his 20s. He also suffered gastrointestinal issues and severe liver disease. He wanted his ailments studied. Now, almost 200 years later, his request has been honored. Besides sequencing his genome from 5 samples of his hair, a careful chemical analysis was carried out. One of Beethoven's locks had 258 micrograms of lead per gram of hair, and the other had 380 micrograms of lead. Normal levels in hair are less than 4 micrograms of lead per gram. Beethoven had 95 times the normal amount of lead in his system. How could this be? One possible source was from the cheap wine he consumed. It was customary in Beethoven's time to sweeten cheap wine with lead acetate, also called sugars of lead. Wine was also fermented in vessels soldered with lead. The lead leached into the wine over time. Apparently, corks were also soaked in lead salts to make them seal better. Please note, I'm not accusing Trader Joe's of using lead acetate or any toxic compounds to sweeten 2-buck chuck. Your body contains only a bit of lead absorbed from the environment. However, it serves no essential biological purpose, and we could easily survive, indeed thrive, without it. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about lead. Lecherous plumber, with an appetite for both acids and bases. In the next program in this series, I'll examine a somewhat less toxic element, bismuth. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element lead.